Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is going to talk about stress transformations. We're going to focus on how stresses transform as we look at a plane stress element and rotate it in the plane of the element. So let's start by looking at what we're going to call oblique stresses. Let's imagine we have a rectangular member loaded with an axial force. Normally, when we write the stress, we'll make a cross-section perpendicular to the force, and we'll calculate the stress in the normal way as simply P over A, where the area is just those dimensions. We could write this a different way by saying that the force is just the stress times the area, where our area is just the width of the element and the thick times the thickness of the element. Now let's say instead we cut a plane that's not perpendicular to the force, but is at some oblique angle. And let's say that that angle is theta degrees, some angle from the vertical axis. Now, as we kind of see here. Now, if we take a look at that a little closer, let's say our dimensions of this thing are B inches tall and T inches wide. What we're generally going to need to do is turn that stress into normal and shear components. We don't really have a way to evaluate stresses that are at some skew angle. So we need to turn them into the normal stress and the shear stress so we can compare them to our allowables, something like FTU and FSU. So we see now we've cut this B dimension where we had an area BT, we now are cutting at some angle. Our width is still T, but our B dimension now changes to B prime. And that change can be evaluated by trig. Okay, so that's what we're going to focus on, calculating those normal and shear stresses. We can see since the original distance was B, or dimension, height dimension, the new dimension is B prime, where B prime cosine theta is B, so we can write that B prime then is just B over cosine theta. Therefore, our area at that cut angle theta can be written this way, as BT over cosine theta. Now, the normal stresses, let's look closer at the normal and shear stresses. We can evaluate the magnitude of those from simple trig. The normal stress is just P cosine theta, and the shear stress is simply P sine theta. Our stresses now are those forces, the normal and the shear stresses, divided by that angled area, which we can plug in that angled area and write the stress like this and simplify it into this form. Now this looks weird and we start puckering up and getting all nervous when we see equations with a lot of trig, even though at some point most students, engineering students and industry professionals, were good at trig. A lot of times once we go through higher learning, we start getting afraid of it and not doing as well. But this is completely doable by anybody that's passed an engineering undergraduate curriculum. Our shear stresses, once again, are that shear stress divided by that inclined area, which can be written this way. So we get these equations for the stresses. Now we could simplify these even further. If we look at that original area that was perpendicular to force, we call that stress on that perpendicular cut sigma, just P over that original area BT, and then plug in P over that area. By all the places we see it here, we can write our stresses in a different form. This is the stress on that inclined face, the normal, and the shear stress on the inclined face, where the normal stress sigma theta is a measure of the tendency for direct separation of that plane, and that shear stress can be thought of as just the measure of the tendency of slippage along that cut plane. These two equations. Now, if we plot these as a function of the angle, different cuts, going from 0, which is a perpendicular cut, all the way to 90 degrees, which means an in-plane cut, we'll see that our normal stress, and in this graph we have normalized it against the original perpendicular cut sigma, We go from a max value at a perpendicular cut down to a minimum value of 0 with a nonlinear distribution. Meanwhile, our original force, there was no shear applied, so our shear stress was 0. But as we incline that angle, if we evaluate the stress at different angles, if we make different cuts, we're going to get more and more shear stress until we reach a maximum value of that normal stress over 2, and then it declines down to 0 again in a parabolic fashion. So that is the distribution of stresses for different cuts within the material. Now this is done less often in industry, especially in the aerospace industry, where we often have lightweight structural parts which carry stresses in only one direction, or like just axial load or just bending or just shear and things like this. However, this is a fundamental principle that we should be able to apply for the times when we run into problems that require us to evaluate stresses at different section cuts. And this little method of evaluating oblique stresses is useful for a uniaxial load. Notice we have a member with a single force, and this can be used for those kinds of problems. We also see from this little graph on the lower right that our maximum shear stress is just the normal stress. It's half the normal stress. This finding of the maximum shear stress for a different cut. So within the plane of this thing, even though it was only applied with an axial force, P over A kind of normal stress, if we had cut it at different angles, we also find that there are shear stresses within the part. And while we're pulling on it, not only is this part experiencing a normal stress, it's also experiencing shear off at different angles with a maximum shear of 45 degrees. So when we fail a part, a ductile material will often elongate and fail in tension, while a more brittle part will often not elongate a measurable amount, and you'll see a failure along these shear planes where the shear is maximum. So if that part stretches, gets thinner and breaks, it looks like it stretched out and then broke, that would mean it's a ductile material and it failed in tension. But if you find out the thing doesn't look like it deformed much and you get a failure at a 45-degree angle, that implies that it was actually shear that caused the failure, and you got a shear failure at 45 degrees to the loading due to that slippage along the maximum shear plane. So these ideas kind of lay the foundation and the findings of a number of advanced topics that we may run into throughout our studies in Structures 2 and beyond. So this is the idea of oblique stresses, and whenever we have a single member with a single force, we can evaluate the stress on other cuts with this approach of just calculating stresses. Got it? Now let's look at a more general stress transformation equation. So we saw in that if we imagine that we have a part that's very thin and it's loaded with stresses along multiple faces. We've got a stress in the X direction. This is a common kind of problem we might see for a skin. If we have a fuselage, we pull an element out of the fuselage, it may experience normal stresses on one face, normal stresses on a perpendicular face, and shear stresses within the plane. Now, often we'll find that third dimension, so we can see we got stress in the X direction, stress in the Y direction, and a shear stress in that plane. We also find it's very common that we have a plane stress condition where our third face, that normal stress in the Z direction, is 0, and if we're relatively small, thin, then we can often ignore the Poisson's effect for that out-of-plane unloaded stress, unloaded face. Now notice our sign convention here. We're following right-hand rule sign convention, so and stress convention. So with this element, we'll see, if we imagine that our positive X is to the right and our positive Y is up, then if we cut the section on the right, on the positive side of X, that's a positive face, and our stress is acting in the positive direction. So we have positive face, positive acting stress, that's a positive stress. On the other hand, we see it's balanced on the negative face, the face that's cut facing in a negative x direction, and the stress in that direction is aimed in a negative direction. So we have negative face, negative stress is also a positive stress, a tensile stress. So they say two wrongs don't make a right, but two negatives do make a positive. And on the vertical face, that's a positive y face in a positive direction is a positive stress tension. On the negative side of that, the negative face acting in a negative direction, that is also a positive stress. The shear stress, now remember with beam sign convention, we were doing deflection of beams, downward chopping off from left to right was a positive shear stress. But for stress transformations, we're following a more rigorous right-hand rule. We've got the positive x face and the shear stress is acting in a positive y direction. Therefore, that's a positive shear stress. On the positive y face in a positive x direction, we have the shear stress. That's a positive shear stress. And then down below, we've got a negative face, negative direction, negative face, negative direction. Those are both positive. So you'll see here, now with shear stresses, remember, they're so romantic. They're always mouth to mouth and toes intertwined. What that means is all we need is one direction of our shear stress to be understood, and all the rest fall into place. If we've got the one on the right is up, that means the one on top is mouth to mouth. On the bottom is toe to toe, and on the other side is toe to toe and mouth to mouth. That's how it works. So for our sign convention here, we're seeing a positive sigma x, a positive sigma y, and a positive shear. If the shear is acting in the other direction, where it's a negative sign we're going to use in our equations. If our normal stress is acting in the other direction, the sigma x, then that would be negative. If our sigma y is acting downward on the upper face, then that would be negative. These are all positive in this case. We have to follow this sign convention religiously in order to implement our equations correctly. Now that we understand the element and the positive identification of our stresses on the element, so we can have a stress on the x face, it can be positive or negative. In this case, it's positive. We can have a stress on the y face. It can be positive or negative. In this case, it's positive. We're going to have a shear stress. It can be positive or negative. In this case, it's positive. Notice I'm not talking about the reacting side. If we have a sigma x, it's going to have to be reacted by a sigma x on the other face, sigma y by sigma I, and the shear stresses accordingly. So we only need to talk about one side, and it tells us what everything is going on. So with this known, we're now ready to develop a more general equation for stress transformations. We're not going to derive it, we're just going to present it in this case. So once again, if we cut an oblique angle on this element, right now these stresses as shown are the stresses on those faces. But if instead we cut off at some angle, once again, so we can look at it as the angle it makes with the vertical axis or the angle it makes with the x-axis. Now notice here we have this element, and now we're chopping it at some angle. So notice here I'm showing the angle at 2 dimensions. If you show your thumb in the x direction and your finger in the y direction, you'll notice at that other orientation what we've done, I'm showing you the angle with the x. As you rotate that with the x, that's the angle we're making with the x. Meanwhile, the angle with the vertical changes by the same amount. If we had our vertical was like, if our axis was like this, x and y, our element is like this, aligned with those axes. Now as we rotate the x by some angle theta, notice the y is also rotating by the same amount. So whether we show the angle on the normal stress as I'm showing here, or whether we show the angle of the cut face as I'm also showing here, those are the same angle theta. Okay, with that said, what we're looking for is the stress, the normal stress on that cut face, and the shear stress on that cut face. Remember, normal is going this way in the x, and now it's moved up on that inclined face, by where the difference between those is that angle. The shear stress was positive going up, and now it is changing, and we got a different shear stress, tau theta, on that inclined face. And we can develop from trig the actual equations in a manner analogous to what we did for oblique stresses, but now we have two stresses to deal with, or actually three stresses. We've got sigma x, which is changing. In our oblique stress discussion in the last slide, all we had to deal with was sigma x and the changing face dimensions. Now we have sigma x and the changing face, tau and the changing face, both affecting our stresses, and sigma y on the element and how that affects that changing face. Sigma x, sigma y, and tau, and how they are acting on that face as we rotate it to get the full stress picture. These are our two equations. We've got sigma theta, which all we need to do is with our original element, we define positive x and positive y. And even though I align this with a horizontal and vertical axis, we can use this equation, this transformation, for any element we find. Just define a positive x and a positive y aligned with the way that element is oriented. And then we can apply these stress transformations, and that will tell us what the stresses are for any other rotation of the element relative to the original element that we have. In this case, our original element has positive x to the right on a horizontal axis, positive y upwards on a vertical axis. So our angle is associated with what angle the new x, or the x theta, makes with the original sigma x axis, the original x axis. That's our theta. From the original x axis to the new x axis, or the theta axis. So sigma theta, we just take our sigma x, sigma y, and our shear stress, which is actually tau xy, even though it's just shown as tau in our picture. So we plug those into here. You'll notice our first term is just the average stress. Our second term is just the difference of stress over 2. And we have some cosine and sine 2 theta kind of terms, which means we take whatever that angle is and multiply it by 2 to plug into our cosine equation. For shear stress on that inclined face, we just plug in our sigma x, sigma y, and our theta and tau into the second equation, and that gives us the shear stress. We can evaluate this element for the stress on that face relative to FTU, and the shear stress on that face relative to FSU. So these equations enable us to figure out how much normal and shear stress we have for any cut through our element. Or, if you please, a different way of thinking about this is no matter how we rotate this element, we can calculate the stress on that new x space, that x inclined face, using these equations. This little sketch helps us to see that. Where the second, we've got the uppermost sketch, which showed our original element. We've got the sketch which shows that cut face. And the third sketch here says, well, if we think of this as just rotating the element, instead of the element being cut out of the skin like this, we cut one like this. And if we want to know what the stresses are on that cut face, that new x face, or that theta face, then these equations will give us sigma theta and tau theta on the inclined face. The easiest way to think of this is point your thumb down the original x-axis, rotate it to the new x-axis, and that's your angle that you're going to plug in here along with the sigma x, sigma y, and tau on that original element. And that will give you your normal stress and your shear stress on the inclined face. It's that simple. Got it? Okay, let's look at a couple examples. Our first little example looks like this. Let's say that we have an aircraft and we yank one little infinitesimal element out of there and find stresses in the x direction. In one direction is 20 ksi, in the perpendicular direction is 10 ksi, and a shear stress of 5 ksi. All these three stresses are acting in the positive direction, so we've got a positive 20,000 x stress, positive 10,000 Y stress and a positive 5,000 shear stress, which is tau xy. We can now plug those into our equations. Now let's say we want the stresses at 30 degrees. All we do is we plug that 30 degrees into our equation with those stress values. So actually, we can use those equations directly, but in this particular case, what I'm doing is showing you what that average stress is and what the difference in stress is. Okay, no problem. And then I'm plugging those values into these equations. I've written this in a slightly different form. And what this does is give us our normal stress and our shear stress. You'll notice the normal stress went up. Let's see, on the X face we had a 20,000 psi stress, and now we have almost 22,000 psi on this new face. Our shear stress dropped from 5,000 to minus 1830. It switched sign there, okay? So that's how we implement this. Now let's take a look at another example. And we can write our results like this. If we take another example, let's say that we pull out an element and we get these stresses. You'll notice these stresses are identical to the last one, but in this case, on the rightmost face, notice our shear stress is acting down. That is actually defined as a negative shear stress, and therefore we plug in a negative value for that stress. We get the same average and difference of stress, but now we find out our normal stress went down and our shear stress is even greater. It's negative. It's going in the other direction now, and it is greater magnitude than it was. So this is how we implement stress transformations for an element that we want to rotate. This is a critical building block for calculating principal stresses, which is something we do quite often in industry, and we're going to cover that in our next video. So study this out, try it out a few times, make sure you understand this before you go to the next sub video looking at principal stresses. Enjoy.